Okay, so in this video, we want to review how to sketch the graph of any logarithmic function where the base is any real number larger than 1. So the idea is, well, let's sketch first its inverse function, a simpler function, namely the exponential function base 8. So let me sketch the graph of y equals a to the x first. And it looks something like this. And a key point of this graph is at 0. A to the 0 for any positive number a is equal to 1. So the y-intercept for any exponential function where the base is larger than 1 will be at 1. And if you don't remember how to sketch this graph for an exponential function, well, it's very easy to rederive it. Again, any positive number to the 0th power is 1. So the exponential function will always cross the y-axis at the value of 1. And if you think about this, in this case, a is any number bigger than 1. So look first at the positive real axis. As x increases, you are considering as a y value a to the x. But as you take a larger and larger power of a number that is larger than 1, this will get bigger and bigger and bigger. Think of a being 2, and think of x taking on integer values. As you let x range from 1, 2, 3, 4, 5, 2 to these numbers will be 2, 4, 8, 16, 32. So this will grow extremely rapidly. So as x increases, a to the x will increase even faster. Again, because taking a larger and larger power of a number that is larger than 1 will grow extremely fast. Now what about the negative real axis? Well, if you think about this, when you take a number to a negative exponent, what you have is the reciprocal of that expression. Let's take here a very simple example. If I give you 2 to the minus 5, this is 1 over 2 to the 5, which is of course 1 over 32. So any number that is larger than 1 raised to a negative exponent will be essentially, by the reciprocal, 1 over a really large number. So as you let x tend to be more and more negative, the exponential function is 1 over a larger and larger value. So 1 over something big is very small, so as x tends to negative infinity, the values here will approach 1 over infinity, which approach 0. So the values will get closer and closer and closer to 0, therefore to the x-axis. So this is how you can quickly sketch the graph of a to the x when a is larger than 1. And again, whenever in doubt, replace a by 2, and the graph will always have the same overall shape and always cross the y-axis at the y value 1. And now you might wonder, well, how will this help us to sketch the graph of the logarithmic function base a? Well, if you remember, the logarithmic function base a is by definition the inverse of the exponential function base a. But once we have the graph of the original function, the graph of the inverse is easily obtained. If you recall, we simply have to sketch the line y equals x, and the graph of the inverse is obtained by reflecting the graph of the original function about the line y equals x. So this will be a mirror image. So think of reflecting the original function about y equals x, creating a perfectly mirrored image of the original function. And one key point is that this point, if you put it here, is the point x equals 0, y equals 1. And when you reflect about y equals x, the x-axis becomes the y-axis, and the y becomes the x-axis, which means the coordinates of this point will change from 0, 1 to 1, 0. So the logarithmic function base a will cross the x-axis at x equals 1. So it will look, try to create a good mirror image, something like this. And this point again is always going to be 1. And the two key features other than this point are, this goes to infinity, infinity, which will go if we flip to infinity, infinity. And if you look here, if you're not sure about the behavior of the logarithmic function near x equals 0, think about what happens here in the limit. We let x tend to negative infinity, and the y values tend to 0 and always remain positive. So for the original function in the limit, we have negative infinity for x, positive 0 for y. But in the reflected image, for the inverse, the x becomes the y becomes the x, so this will become 0 plus for x, and negative infinity for y. Which now tells you that when x is very small but positive, the y values of the logarithmic function will be very large and negative, so you will have a vertical asymptote around 0, where the function shoots down to negative infinity, and when x goes to positive infinity, the logarithmic function will also tend to positive infinity. It grows very slowly, but it grows out of bounds. And this is how you can quickly obtain the graph of the logarithmic function base a, as it is the inverse of the simpler graph of the exponential function base a. And that's it.